Let's see if we can tie this all together by doing an example, a numerical example, where we will use a transfer function and the frequency response function of a low-pass filter to process a time domain function that's been expanded into its Fourier series. And we'll do this all in the frequency domain. Start out in the time domain, go into the frequency domain, and then bring it back into the time domain and just show how this all fits together. So first of all, we know that the transfer function h of s was defined as the ratio of the output to the input of the Laplace transforms. And we know that when we replaced s with j omega, what we ended up with was a frequency response function which represented the steady state, the way that we would represent the circuit for steady state analysis. And that then becomes h of j omega, which is equal to V out of j omega over V in of j omega. Now, we multiply both sides of this equation to get then that V out of j omega, which is the frequency spectrum of the output, is equal to the frequency spectrum of the input, V in of j omega, times the frequency response function. Now, these are all complex expressions, which can be written in their polar forms as a magnitude and a phase. In other words, V out of j omega can be thought of as a magnitude of V out of j omega and some angle theta out of j omega is equal to the magnitude of V in of j omega, angle theta in of j omega, times the magnitude of the frequency response function h of j omega and an angle theta sub h of j omega. So what we're saying is we've got this product here, and we're just writing them in terms of their polar coordinates, magnitude and phase, magnitude and phase. Now in the polar form, we know that when you're multiplying two things in the polar region, in polar form, it's going to be the magnitudes multiplied together, the magnitude of V in of j omega times the magnitude of h of j omega, and then the angle will be the angle of theta in of j omega, theta in of j omega, plus the angle of the transfer function, theta sub h of j omega. So this then is the magnitude on the right side. The magnitude on the left side must equal the magnitude of the right side. We then have the magnitude of the output. The magnitude of the frequency spectrum of the output is equal to the magnitude of the frequency spectrum of the input times the magnitude of the frequency response function, h of j omega. And theta out of j omega then is equal to the phase of the input plus the phase of the frequency response function. In other words, we'll be able to calculate the amplitude of each of the different frequencies at the output by taking the amplitude of each of those frequencies at the input and evaluating them and multiplying them by the frequency response function evaluated at those frequencies. And similarly, we'll be able to determine the phase shift of each of those frequencies at the output by taking and adding to the phase of the input the phase of the frequency response function at those frequencies. So here we go. The input function that we're going to use is going to be a square wave function that we're going to represent as its Fourier series expansion. Now, the Fourier series expansion involves an infinite number of terms. We're not going to do an infinite number of terms. We're going to limit ourselves to the first 5 terms and call that good. It'll at least demonstrate the concept. Again, you can add as many terms in as you want for as much accuracy as you want. The circuit that we're going to run it through is going to be a low-pass filter that we've talked about in Chapter 14. It is characterized by a magnitude, which is 1 over r times c divided by the square root, thus. That gives us the magnitude of the frequency response. And then we have the phase of the frequency response function, which is given by this. So, the b sub k's we have seen, the b sub k's for a square wave, are equal to 4 times v sub m divided by k times pi, where k is only odd values. So k equals 1, 3, 5, 7, 9, and so on. And for this square wave, omega naught is equal to the omega naught is equal to 250 radians per second. For the input function, b sub k again is equal to that. We're going to do just the first 5 components, which corresponds to k equaling 1, 3, 5, 7, and 9. The frequencies associated with that are going to be k omega naught again, just omega naught is equal to 250 radians per second. So the first component would be 250, the third would be when k equals 3, or 3 times omega naught is 750, 5 times omega naught is 1250, 7 times omega naught is 1750, and 9 times omega naught is 2250 radians per second. At those frequencies, or at those component numbers, k equals 1, k equals 3, 5, 7, and 9, b sub k is equal to these values for a v sub m equaling 2 volts. Thus, at the input, we can approximate this square wave, and it's only approximation. It would have an infinite number of terms if it's going to be exact, but we can approximate it by this b sub k times the sine of 250t. The amplitude of the input of that component is 2.5465 sine of that, plus that b sub k, b sub 3, that b sub 5, that b sub 7, and that b sub 9. To think of this in the frequency domain, its frequency spectrum Vn of j omega then is simply equal to each of these in their phasor or their frequency representation. This would be 2.5465 angle 0. That's the frequency representation of the term at 250 radians per second, plus 0.8488 angle 0, plus 0.5093 angle 0, plus 0.3638 angle 0, plus 0.2829 angle 0. It should be pointed out that because all of these terms are sine terms, we're going to take them into the frequency domain as written, not add the 90-degree phase shift to turn them into cosine terms. But when we come out of the frequency domain at the end, we'll just remember that all of these angles, the angles of the output, will be relative to a sine term rather than a cosine term. This then represents the frequency, the frequency spectrum of the input, and it consists of one value at omega equals 250 with an amplitude of 2.5465, another one at omega equals 750 with an amplitude, I drew that too big, with an amplitude down here at 0.8488, another one of 0.53 at 1250. It has a value of a single point there of 0.5093, and getting even smaller as we go down, 0.3638 at 1750 radians per second, and then even smaller at 0.2829 amplitude for the 2250 radian per second component. So this is how we represent the input, or the input spectrum. Now, we've seen this. This is the frequency response of that filter that we're talking about. It's defined for all frequencies. But because our input only exists at 5 frequencies, we're really only interested in 5 values of this corresponding to 250, 750, 1250, and so on. This is the magnitude term. Similarly, the phase of that filter, the phase of theta, or theta sub h of j omega, is this entire thing, but once again, because we're only interested at the 5 components that exist in the input, we will be looking at these phase shift values corresponding to those frequencies there. Okay, let's recall what it is that we're doing. We're wanting to calculate the output, the how should we say, the spectral output, the spectrum of the output, which we're going to get the magnitude of it by multiplying the magnitude of the transfer function times the magnitude of the input spectrum, or the magnitude of V out of j omega, that's the spectrum of the output, is going to equal the magnitude of h of j omega times the amplitude of the input spectrum. Where, and this is the transfer, or this is the frequency response, where for this case omega sub c is equal to 1 over r times c. And the phase terms are going to equal the phase of the output of j omega is going to equal the phase of the input of j omega plus the phase of the frequency response function of j omega. But keep in mind, our inputs, coming back here, our inputs all had 0 degree phase angles associated with them. We were setting the source as the reference for our phase angle. So the inputs all have angle zeros as their phase term in the spectrum. So this is just going to be equal to 0, and the phase of the transfer function here is equal to negative tangent, or negative arctangent of omega over omega sub c. So the theta of the output then is going to be 0 minus the arctangent of omega over omega sub c. Again, omega sub c is equal to 1 over rc. So to do this calculation, V out, I needed an equal sign there. V out is equal to the magnitude of h of j omega times the magnitude of the input. Well, you can go back a couple of slides and notice these values, the magnitudes of the input. I've shown those here at the frequencies that they exist. So this line drawing here, this line graph, represents the magnitude of the input spectrum. The first term at 250 radians per second has a magnitude of 2.5465. Similarly, the magnitude at 750, this is the k equals 1 term, the k equals 3 term, and so on. So these top numbers are the values of the magnitudes of each of the input components. These other numbers are the values of the magnitude of the frequency response function at each of these frequencies. In other words, these numbers here are just this evaluated at omega equals 250, omega equals 500, 750, and so on. So what this is telling us then is that we can calculate the magnitude of each of the components in the output by taking the magnitude of the frequency response and multiplying it by the magnitude of the input for each of these different frequencies. So this times this, and this times this, and this times this, and this times this, and this times this will give us the amplitudes for each of the corresponding frequency components at the output. That's the magnitude. Now the angle is simply going to be, the angle of the output is going to be the angle of the input, which was 0, plus, in this case, the term at 250 radians per second. The filter is going to add a 27 degree phase delay for that frequency. It introduces a negative 56 degree phase delay for the 750 radians per second. At the 1250 radians per second, it's up to a negative 68, or a delay of 68 degrees. Then 74 degrees at 1750, and 77 degrees at 2250. And again, those are the first 5 terms that we're going to be interested in for this example. So this is just that same graph that we were looking at before, where each of these numbers corresponds to the amplitude of the input for each of those frequencies. These numbers represent the magnitude of the frequency response. And we said then that the magnitude of the output is equal to this number times this number, or 0.9 times 2.5465 equals 2.2776. So at 250 radians per second, the input had an amplitude of 2.5465 volts. The output had an amplitude of 0.9 times that, or 2.2776 volts. So you see that there is a slight amount of attenuation, about 10% in fact. We know it's 10% because this amplitude here was 0.9. So that represents about 90%. About 90% of this frequency component makes it through the filter. On the other hand, only about 55% of the second component, the k equals 3 component, makes it through, where we've got the 0.55 times that gives us 0.47. Here, only 38% of the original signal makes it through. Here, 27% of the original signal makes it through. Here, only 21% of the original signal makes it through. In other words, the higher the frequency, the more those components are attenuated. So at the output, the amplitude of the 250 radian per second term is 2.277. Did I get that right? I typed that in wrong. 2.2776 it should be. Similarly, the amplitude of the 750 radian per second term is 0.47064, 0.18915, 0.0999, and 0.06137. 9 or 0.0614, rounding that one off. Now, the phase terms. You'll recall that the phase of the output was equal to the phase of the input plus the phase of the frequency response. But because the phase of the input was 0 in each of these terms, the phase seen at the output is just the phase shifts, negative 27, the phase shifts introduced by the frequency response function, or negative 27, negative 56, negative 68, negative 74, negative 77, and they show up then as the phase shift at each of those corresponding frequencies. Notice that the higher the frequency, the greater the phase shift. This variation in phase shift for the different frequencies is what is known as phase distortion. Thus, we have reconstructed the output that results from those 5 inputs, those 5 components being put into that low-pass filter. Let's look now at each of the 2 different time functions, and we'll talk about this red one. First of all, the blue function is our approximation to the square wave. There are only 5 components. The actual square wave should have been something like that, but to have had it be that, we would have had to have added an infinite number of components. That would take too long. So we're approximating it by the first 5. Now, the green graph here is V out of t, or our approximation of V out of t being approximated by those 5 terms. Notice that at t equals 0, the square wave would have just shot right up. You'll notice that there is a phase shift, approximately 27 degrees, of this fundamental or lowest frequency. See, this lowest frequency, that's the same frequency as the square wave. That's what's known as the fundamental frequency of this square wave signal. And there's a phase shift. Now, it's kind of hard to see, but as these other terms start to kick in, 56 degrees, 60, 68 degrees, 74 degrees, and with significantly reduced amplitudes, what you see is some variation starting to happen, and that this whole thing continues to be delayed, the fundamental continues to be delayed by that 27 degrees. So this green represents the phase distorted, phase shifted output with a amplitude as shown. Now, this third red graph, this graph is simply meant to show what it would be if it wasn't for this phase distortion. The red graph, you'll notice, is completely in phase with the blue. So this shows just the magnitude itself if there was no phase shifting being involved. And again, it just shows that it lines up with the square wave. The actual is phase shifted because of the delays introduced by that filter.